In the last lecture, we were establishing the relationship between Hotellings T2 statistic and the likelihood ratio statistic, and we had considered that x1, x2, xn is a random sample from a multivariate normal distribution with mean vector as mu and a covariance matrix positive definite sigma, and we were looking at this null hypothesis to be tested that mu equal to a null vector against an alternate hypothesis that mu is not equal to a null vector, and we had derived the likelihood ratio statistic lambda, which is given by supremum under script theta naught, where script theta naught was the parameter space under the null hypothesis of the likelihood function L mu sigma, that divided by the supremum of the likelihood function under script theta, where script theta is the unrestricted parameter space, not restricting oneself to the null hypothesis space. And then we had come up to the point that we had shown that this lambda to the power 2 by n is equal to determinant of A divided by determinant of A plus n times x bar transpose. So we continue from this particular point. We have this lambda to the power 2 by n that is given by determinant of A that divided by determinant of A plus n times x bar transpose is determinant. Now what we can do here is that we can take determinant of A outside from this denominator to get to the form that this is determinant of A. So if we take A outside here, what we'll be having here is Im, that's the dimension there, this plus n times A inverse and x bar transpose its determinant. So that this term is just equal to 1 upon determinant of Im plus n times A inverse x bar transpose. Now we note that we have a following result, that if we are looking at determinant of I, say of p dimension, IQ minus Q, a matrix, and a matrix P here. Now the dimension of this P is P by Q, and the dimension here is Q rows and P columns. So this determinant can be written as IP, this plus P times Q, that using the result of this partitioned matrix's determinant. This is also IQ plus Q times P. Now in this expression here, if we use this same result here, we will take this term as, say, P matrix. This actually is a vector. This is an m by 1 vector, and this is a Q which also is a vector. So we will be able to write, using this result here, this lambda to the power 2 by n, that is equal to 1 divided by determinant of I1. So it's basically a scalar quantity, it's just equal to 1, that plus Q times P. So we can interchange this and we can write this as, now this note that this n is a scalar quantity. So what we'll be having here is x bar n times x bar transpose A inverse and x bar, determinant of that. Now this is a scalar quantity, this also is a scalar quantity, so this is nothing but 1 plus n x bar transpose A inverse x bar to the power minus 1, right? Now we will see what's the relationship of this with a t-square statistic. Now the corresponding t-square statistic, if we have h naught, mu equal to a null vector, this is to be tested against an alternate hypothesis that this mu is not equal to a null vector. We will have the distribution of x bar to be a multivariate normal with the mean vector as a null vector and a covariance matrix as sigma by n, this under h naught. And what more is n minus 1 times s with the divisor n minus 1, let us write that to be equal to A, which is actually equal to A. This would follow a Wishart distribution on M dimension with the degrees of freedom as n minus 1 and an associated variance covariance matrix as sigma. So what would be the t-square statistic from here? So if we have this setup, then the t-square statistic is given by t square, which is, if we recall the result, that t square, how t square is formed from a Wishart distribution and a multivariate normal distribution. This would be given by n times n is the degrees of freedom of the associated Wishart, which is n minus 1, times this x bar transpose, and then this Wishart matrices inverse x bar. So this statistic is going to be given by this, and hence this would imply that this t square by n minus 1, this is equal to n times x bar transpose A inverse x bar. So t square by n minus 1 in case of testing from a multivariate normal distribution with mean vector equal to a null vector is going to be given by this. And thus, if we have this lambda to the power 2 by n to be given by this, actually, as we can see, is same as what we have obtained out here. So this would imply that this lambda, let me take that 2 by n to the other side, and let me first keep it in the form that it was. This would be given by 1 plus t squared, the observed value in case of small x bar, and the associated A matrix. So this is t square by n minus 1 whole to the power minus 1. This would further imply that the likelihood ratio statistic is going to be given by 1 plus t square by n minus 1 whole raised to the power minus n by 2. So if this is the relationship between the likelihood ratio statistic and the Hotellings T square statistic, we can say the following, that the likelihood ratio test would reject the null hypothesis. Likelihood ratio test for testing this H naught mu equal to a null vector against the alternate hypothesis HA, that mu is not equal to the null vector if lambda is small. That's how a likelihood ratio test goes along, because it's looking at the ratio of the two supremums. One in the denominator is supremum over the null space, and the one in the denominator is a supremum over the entire parameter space, not restricting oneself to the null space. So the likelihood ratio test would reject if lambda is small. This is equivalent because we have this relationship that this lambda is 1 upon 1 plus t squared to the power n by 2, and hence lambda being small is equivalent to saying that t square is large, and that's what is the desired thing. So this is equivalent to saying that if t square is large. So this would imply that the testing based on t square is equivalent to the testing procedure based on the likelihood ratio principle, likelihood ratio statistic, right. So the two actually are equivalent. This gives us another justification actually of the t square, Hotellings T square statistic, that if we are looking at using the Hotellings T square statistic for testing such null hypothesis as what is framed, that testing procedure is equivalent to a likelihood ratio test principle. Now, if this lambda, what we have derived is this particular quantity, we can derive the distribution of this lambda or we can use an asymptotic distribution. Now the distribution of lambda is going to be based on the distribution of t square. T square, remember, under the null hypothesis has got an F distribution on m n minus m plus 1 degrees of freedom, and hence the distribution of this lambda can theoretically be derived when we have the relationship between this lambda and t square. For large sample, asymptotic test based on this likelihood principle can be obtained. Asymptotic test based on LR, likelihood ratio, is going to be given or rather would be based on the following fact, that this minus 2 log lambda, this would follow a central chi-square on the degrees of freedom, which is the difference of the dimension of script theta and the dimension of script theta naught. So this minus 2 log lambda, where lambda is given by this likelihood ratio, which is this particular quantity, one can look at what is this degrees of freedom now. Now what is the dimension of script theta and dimension of script theta naught? Let me write the two spaces so that it would be easy to see what is the dimension of the two spaces. So this is mu sigma space, where this mu belongs to r to the power p, and this sigma is positive definite. It's a symmetric matrix with p into p plus 1 by 2 distinct elements, and script theta naught is the null space, which is the set of all mu sigmas such that mu under the restriction of the null space is a null vector, and this sigma is still positive definite. So the dimension of script theta would be the p dimensions that are present in mu, this plus the number of free parameters in sigma, which is p into p plus 1 by 2, and the dimension of script theta naught, this is equal to p into p plus 1 by 2, the distinct elements corresponding to this sigma matrix, and mu is specified, and nothing comes actually from there. So this would imply that minus 2 log lambda would follow asymptotically a chi-square random variate on just p degrees of freedom. Now we will reject the null hypothesis, reject H naught if observed value of this test statistic, that is minus 2 log lambda, the observed value of that is greater than chi-square p alpha, where this is the upper alpha percent cutoff point of a central chi-square on p degrees of freedom, right. So this is the asymptotic test that is based on the likelihood ratio principle, which of course we have shown that it is equivalent to the test that is going to be based on the Hotellings T square statistic. Now let us look at this normal 2 sample problem and how to use the Hotellings T square statistic in order to perform testing in this situation. Normal 2 sample problem. What's the problem here? We have 2 multivariate normal populations, say N, P, I've been using an M, so let me stick to that particular notation, that multivariate normal with a mean vector as mu1 and a covariance matrix as sigma. So this is population number 1, this is population number 1, and the second population is multivariate normal M with a different mean vector and the same covariance matrix sigma. So this is what is characterizing the second population, right, and sigma of course is positive definite. We have this common assumption that sigma is positive definite for the 2 populations. So we have 2 multivariate normal populations differing in their mean vector, and the covariance matrix are same. Suppose now in this particular situation the point of interest is to test the following null hypothesis, that this mu1 vector is equal to mu2 vector. This is to be tested against the alternate hypothesis that this mu1 vector is not equal to this mu2 vector. It is a standard testing procedure. If we look at the corresponding univariate counterpart, then clearly the univariate counterpart also we have done the testing, of course, in univariate counterpart when we have two univariate normal populations with same variance and different mean component. Then the testing of that, of course, is obtained using the t statistic, the student's t statistic, and this we are going to show that the testing of this particular problem in the multivariate multivariate normal population can also be obtained using a Hotellings T squared statistic. Now, suppose we have two sets of random samples now. Suppose x1 1, x2 1, x1 and 1 be a random sample from the first population, which is n m mu 1 sigma, and we have a second set of sample from the second population, x21, x22 and x say n2 to be a random sample from the second multivariate normal population, that is, it is a random sample from mu2 sigma. So, we will be using this two sets of random samples. This is the set of random samples n1 size from the first population. This is the set of random sample from the second population of size n2. Now, if we have this particular setup, then the following can be easily said, that suppose x1 bar is 1 upon n summation I equal to, I am sorry, this is 1 upon n1. So, I am looking at the first population, I equal to 1 to up to n1 of this x1 I. So, this is the sample mean random vector from the first population. This has got a distribution multivariate normal m with a mean vector as mu1 and a covariance matrix as sigma by n1. Now, similarly, we have the second population giving us this mean vector, sample mean vector based on the n2 random samples from the second population. This is 1 upon n2 summation I equal to 1 to up to n2 xi, the random samples from the second population. So, this will follow a multivariate normal similarly with a mean vector as mu2 and a covariance matrix as sigma by n2, right. Now, these two are going to be independent. Why? Because this x1 bar is based on xi1 terms, n1 of them, and this is going to be based on the other set of random sample from the second population. Now, these being set of random samples, this and this. So, this set of random sample is independent of this set of random samples, and within the random sample sets actually this x1 1 would be independent with each of them. So, this set is also set of independent random vectors, and this set also is independent random vectors, and the two are mutually independent because they are random samples from two different multivariate normal populations. So, we have first of all this particular result. Now, corresponding to the sample variance covariance matrix, what we can say is that n1 minus 1 times S1, where S1 is the sample variance covariance matrix based on the set of n1 random samples from the first population, this would follow a Wishart distribution on degrees of freedom as n1 minus 1 and a covariance matrix as sigma, and similarly based on the second set of random samples n2 minus 1 times S2, this would also follow a Wishart distribution, Wishart m, n2 minus 1 and sigma. Now, once again these two are independent, and what is more important is to realize that this x1 bar is independent of S1. That is the result that we have proved for multivariate normal distribution. x2 bar is independent of this S2 quantity, so that what we can further say that all these four statistics, they are mutually independent. First of all, from the set of random samples of size n1, this x1 bar and s1 are independent. From the set of random samples of size s2 from the second population, this x2 bar and s2 are independent, and they are mutually independent because they are random samples from two different multivariate normal populations. So this is what these are the building blocks for getting into the Hotellings T2 statistic for this particular setup. Now let us look at the distribution of this x1 bar minus x2 bar. What is going to be the distribution of this? The distribution of this, we have x1 bar to be this multivariate normal, x2 bar to be this multivariate normal distribution. The two are independent, so one can very easily show that this also is following a multivariate normal distribution, m dimensional, with mu1 minus mu2 as its mean vector, and the covariance matrix would just be the sum of the two covariance matrices because x1 bar and x2 bar are independent. So what is it? That is equal to sigma times 1 upon n1 plus 1 upon n2. So this is 1 upon n1 plus 1 upon n2. Now this would follow under the null hypothesis that mu1 is equal to mu2. This would follow a multivariate normal with a mean vector as null vector and a covariance matrix as n1 plus n2 by n1 n2 times sigma. This is the distribution under the null hypothesis H naught being true, right. So this as far as combining the two sample mean vectors. Now what can we say further is that consider the pooled sample variance covariance matrix. Consider the pooled sample variance covariance matrix. That would be given by S, which is 1 upon n1 plus n2 minus 2. This is actually same as that type what we usually do in univariate theory also. So that would be the pooling here 1 upon n1 x I1 minus x 1 bar. So this is for the part that is coming from the first set of random samples. So it's xi1 minus the mean coming from all these xi1 quantities, that multiplied by xi1 vectors minus x bar 1 vector transpose, this plus the second set of random samples I equal to 1 to up to n2 x I2. So these are based on the second set of random samples, deviation taken from the second the random mean vector, the sample mean vector based on the second set of random samples. This is x1 xi2 minus x bar 2 its transpose, right. So this is the pooled sample variance covariance matrix, and what is this term equal to? This term is nothing but n1 minus 1 s1, so that we can say that this is n1 plus n2 minus 2 times s. This is equal to the first term, which is n1 minus 1 times s1 plus n2 minus 1 times s2. So we have these two, the sum of these two giving us n1 plus n2 minus 2 times the pooled sample variance covariance matrix. Now what can we say about the distribution of this? Note that this quantity here follows a Wishart distribution, Wishart M, n1 minus 1 degrees of freedom and an associated variance covariance matrix as sigma, and similarly the second part here, this follows a Wishart distribution with the same dimensionality. As the degrees of freedom changes, it is n2 minus 1 and the same variance covariance matrix as sigma. Now the two are independent. That's what we had said in the previous slide here, that these two statistics, they are going to be independent because they are based on two different random samples, and hence this is just the sum of two independent Wishart distributions. Now, by the additive property of the Wishart distribution, keeping the dimensionality and the associated sigma, the associated variance covariance matrix to be same, we will have this particular sum of two independent Wishart distributions with the same dimension and same sigma. This will have a Wishart distribution M, and the degrees of freedom pulling up. So, it is N1 plus N2 minus 2 degrees of freedom, and the same variance covariance matrix as sigma. That is, what we now have is N1 plus N2 minus 2 times this pooled sample variance covariance matrix to have this particular distribution. Now, we now have the building blocks for getting into the Hotellings T2 statistic. One building block is here, and the second building block is basically here, right, because we have one part here, a multivariate normal distribution, and we have another, a Wishart distribution. Now, critically, this multivariate normal distribution and this multivariate normal distribution and this Wishart distribution, they are going to be independent. So, let me write it in a compact form here, that this x1 bar minus x2 bar, this is a random vector. This follows a multivariate normal distribution M with a null vector as its mean vector under the null hypothesis, and this N1 plus N2 divided by N1 N2 times sigma under H naught. We are looking at it under H naught because anyway we will have to look at the distribution of the test statistic, which is going to be Hotellings T2 under the null hypothesis. Otherwise, this remains mu1 minus mu2. This, and we also have N1 plus N2 minus 2 times S, this to follow a Wishart distribution, Wishart M, degrees of freedom as N1 plus N2 minus 2, and an associated variance covariance matrix as sigma, and the two are independent, right. So, we can use, let me write once again what we are now going to recall. We are going to recall that if S has a Wishart M n sigma and D a random vector, this is how we had defined a Hotellings T2 statistic. We have D a random vector which is having a multivariate normal with a mean vector as a delta and a covariance matrix as a C inverse sigma, where C is a scalar quantity. If we have these two random vector and random matrix are independent, then this T2 statistic was given by C times N D prime S inverse D, right. This is how we had defined Hotellings T2. So, this is Hotellings T2 on n degrees of freedom. The degrees of freedom is associated with this n here, which is the degrees of freedom of the associated Wishart distribution. So, if we have that, furthermore what we will be having is T2 by n into n minus m plus 1, that divided by m, this to follow a non-central F distribution on m n minus m plus 1 degrees of freedom, and a non-centrality parameter equal to tau square, which is going to be given by C times delta prime sigma inverse delta. So, this is what is the definition and the distribution of a Hotellings T2, which can be framed from a Wishart distribution and a multivariate normal distribution, the two being independent. So, we are going to use this definition and the distribution of the Hotellings T2 statistic in order to frame the Hotellings T2 statistic out of this particular problem. So, this would imply that the T2 for the given problem would be given by what is C here. C is the inverse of this particular quantity. So, that is N1 N2, this divided by N1 plus N2. So, that is our C term, and then what is N in our problem? N is the degrees of freedom associated with the Wishart distribution, which is in our case N1 plus N2 minus 2. So, we have taken care of these two terms. What is D prime? d prime is the prime of this particular term here, because that is the multivariate normal distribution out there. So, we will have this x1 bar minus x2 bar transpose, and then we have S inverse. S inverse, S is what? S is the associated Wishart distribution. So, we will have that as n1 plus n2 minus 2, this multiplied by this S, the pooled sample variance covariance matrix, inverse of that, and that multiplied by this D. So, this D is once again this x1 bar minus x2 bar, right. So, this is now our Hotellings T square. This is the Hotellings T square for the given problem, for the given 2 sample normal problem. Hotellings T square on how many degrees of freedom? The degrees of freedom would be associated with the degrees of freedom of the underlying Wishart distribution. So, this is an Hotellings T square on n1 plus n2 minus 2 degrees of freedom. So, what happens here? This term cancels out with this term, and whatever remains is the Hotellings T square statistic. That is, this T square is nothing but this n1 n2, this divided by n1 plus n2, this times x1 bar minus x2 bar, its transpose, S inverse, where S is the pooled sample variance covariance matrix, x1 minus this x2, right. Now, furthermore, we will have to find the distribution of this T square or some constant times this T square function. In order to find the distribution of that, what we are going to use is this result for the general Hotellings T square distribution. So, that we will have this T square, now T square divided by what here? Divided by n. What is n? N is the degrees of freedom associated with the Wishart distribution. So, we have n1 plus n2 minus 2, which is now playing the role of n. Then we have the constant here, which was n minus m plus 1. So, that this is now our n minus m. M is the dimension. So, m remains as it is, this plus 1, this divided by m. So, this is equal to, this is going to follow an F distribution on what degrees of freedom? Degrees of freedom is, first is m, and the second is this is n1 plus n2 minus 2 minus m plus 1. So, this is equal to n1 plus n2 minus m minus 1, right. And what is the non-centrality parameter? The non-centrality parameter of this F distribution, if at all, that would be given from this particular mean vector here mu. So, that is going to be this null vector prime, the inverse of this into the null vector, and which is equal to 0. So, this is a central F distribution on these degrees of freedom. So, if we have the Hotellings T square, which is from the 2 sample normal problem, to have this particular distribution, we will reject the null hypothesis. We know its distribution. This is under the null hypothesis. This is under the null hypothesis. So, if it is not under the null hypothesis, then what we will be having is this to be a non-central F distribution, and the non-centrality parameter in such a situation would be given by mu1 minus mu2 prime, and then inverse of this particular quantity, that is n1 plus n2 by n1 n2 into sigma whole inverse, that multiplied by mu1 minus mu2. That would be the distribution or rather that would be the non-centrality parameter of the F distribution if this is not considered under the null hypothesis. Now, using this, what we can do is to look at the rejection region. So, we will reject H naught, which is mu1 equal to mu2 against the alternate hypothesis HA, which is mu1 not equal to mu2 if observed value of this T square divided by n1 plus n2 minus 2, this multiplied by n1 plus N2 minus M minus 1, this divided by M is greater than the upper alpha percent tabulated value of the central F distribution on N1 plus N2 minus M minus 1 degrees of freedom. So, this is the upper alpha percent cutoff point of a central F distribution on M N1 plus N2 minus M minus 1 degrees of freedom. And thus, this testing of this problem of testing this null hypothesis against this alternate hypothesis here would be achieved, and we will reject the null hypothesis if the observed value of this quantity, the test statistic, exceeds the tabulated value, and we accept H naught otherwise. So, that completes the proof actually, or rather the derivation of the test statistic and formulation of this particular testing problem in case of two sample multivariate normal population. We have seen how this testing problem can actually be framed, and testing can be carried out for one sample multivariate or rather one population multivariate normal problem and two population multivariate normal problem. Let us now look at some practical data in order to see how this particular concept of Hotellings T square can be applied for real life data. So, applications of Hotellings T square is what we are now going to see from some real life data examples. These are standard examples. Hotellings T square. We will look at two examples. As I said that these are standard examples. Now, the problem is the following. We have patients of diabetes are given a certain drug and the changes in blood sugar level let that be denoted by variable x1, systolic let us denote that by x2 variable, and diastolic say x3 variable. Pressures are recorded. So, the problem is the following. It is a practical data example that there are patients, say n of them, having diabetes, are given a particular drug, and then in order to judge whether the drug is effective, the following three variables are recorded. The recording on the three variables are taken. The three variables are blood sugar level, changes in the blood sugar level, changes in the systolic pressure, and the changes in the diastolic pressures are recorded. Now, what is the structure of the data? The data looks like the following. Suppose I have got these as subjects, that is patients. We have n such patients. So, these are n patients. The data are recorded for these n patients on the three variables. There are three variables x1, x2 and x3. So, corresponding to these three variables, corresponding to the subject 1, we record that patient's change in the blood sugar level and record it out here, that patient's change in the systolic pressure here, and the change in the diastolic pressure here. So, we will be able to complete this particular data completely. So, this now is a 3 by n data matrix which holds all the recording for the n patients on these three variables of interest. Now, the problem is framed, or rather the question that is posed is whether the drug which was administered on these n patients looks as if it is an effective drug or not. So, the question in hand is to answer is the following. We are interested in testing the hypothesis that the drug which is administered, which is under study, has made no difference with respect to the three variables, that is, the changes are not significant, that is, the changes are not significantly different from 0, are not significant. This is to be tested against that it has made a change, or it has a significant effect. It has a significant effect. So, this basically is the problem, practical problem. Now, in order to test this particular or rather carry forward this particular problem and then use this particular data in order to answer the question of interest, that whether the drug at all is effective or not, that is going to be tested on the basis of the three variables that we have taken recordings on. We assume the following. We assume that this x3 random vector, which is comprising of this x1 variable, x2 variable and this x3 variable, this follows a three-dimensional normal distribution with a mean vector as mu and a covariance matrix as sigma. So, this is the mean vector corresponding to this random vector out here. So, the first component would correspond to the expected change in x1 variable in that multivariate normal population. Now, in terms of this assumption that we have made on this random vector, if we are interested in testing the hypothesis that the drug had made no difference, that is, the changes are not significant, these are the variables denoting the changes in the respective variables. So, the hypothesis of interest is thus the testing of H naught. What is that? It is testing for this change vector in the population being a null vector. This is to be tested against the alternate hypothesis that this mu vector is not equal to a null vector. Now, the problem looks in a tractable form now. So, if we have made this particular assumption and translated this particular hypothesis in terms of the mean vector of this multivariate normal population, we can use a Hotellings T2 statistic in order to test this practical problem. Use Hotellings T2. In what way? What are the things that we will be requiring? We will be requiring as the constituent elements as this x bar to have a three-dimensional normal distribution with a mean vector as null vector under the null hypothesis and sigma by n to be its covariance matrix, right. So, this is under the null hypothesis that the mu vector, the mean vector mu is equal to a null vector, otherwise this would be just a general mu vector. And what more, we have a random sample of size n. So, we will have n minus 1 times s. S is the sample variance covariance matrix with a divisor n minus 1. So, this will have a Wishart distribution now, 3 dimension with the degrees of freedom as the number of samples that has been taken n minus 1 and the covariance matrix as sigma, which is of course unknown. The two are going to be independent from the multivariate normal sampling distribution theory. So, this is what we have already. So, using these two, we can frame a Hotellings T2 statistic, which is going to be given by n times degrees of freedom into this x bar transpose. The mean vector is a null vector and this is an n minus 1 times s whole inverse of that multiplied by this x bar vector. So, what we have these two cancelling out and this is our good old Hotellings T2 statistic, that is n times x bar s inverse x bar, right. Now, furthermore, we will have this T2 this t square divided by its degrees of freedom. Degrees of freedom is n minus 1. Then this is n minus m. M here is 3. This plus 1, that divided by 3. This would follow a central F distribution under H naught on degrees of freedom as 3. And what is this equal to? This is n minus 1 degrees of freedom minus m, that is 3 plus 1. So, this 1 cancels out, plus 1 and minus 1. So, we will have this as n minus 3, this under H naught. So, we have the null distribution of t square, this divided by n minus 1 into this n minus 3 by 3. This follows a central F distribution 3 n minus 3 under our H naught, right. So, if we have this particular term here from the data is this. So, we will have the data as this, say x 1 1, x 2, x 1 2, say. It is the way that we write it. It is no unique way of representing this indexes. So, these are basically the small xi's are the data that we have in our hand. So, given the data which is x1, this is 3-dimensional vector. So, this is the recordings or the record for patient number 1. Then we have this x2 vector, these are the actual recordings. So, this is xn, this is the 3-dimensional record for patient number n. So, these are the data. So, given this particular set of information, we compute x bar, the sample mean, and well, this is going to be given by 1 upon n summation I equal to 1 to n of these xi vectors and the S matrix with a divisor n minus 1. So, that is given by I equal to 1 to n xi minus x bar, xi minus x bar, it is transpose, the random matrix, and this is actually the observed sample variance covariance matrix. So, given these two, one can easily compute this t square observed. T square observed would be n times x bar transpose, this S inverse and this x bar, right. And we will reject, once this is computed, we have the testing, reject H naught, that our mu vector is a null vector, reject H naught equal to a null vector against the alternate hypothesis H A, that this mean vector is not equal to a null vector at level alpha, say, if we have observed value of this t square divided by, what was it? It was t square by n minus 1, n minus 3 by 3. Now, once we have computed this, this is t square observed. So, if this quantity, now we will reject the null hypothesis if of course t square is large, because that is what is going to give us the more deviation from the null hypothesis point, and hence we will reject the null hypothesis if this observed value of this quantity here exceeds the tabulated value of this F distribution on 3 n minus 3 degrees of freedom at alpha point. So, this is the upper alpha percent cutoff point of a central F distribution on 3 n minus 3 degrees of freedom. So, that is how we obtain from the given data this testing problem. Now, let us look at example number 2. This also is a standard type of example that one comes across in real life examples. So, that this is this problem, that n persons suffering from frequent headache are given P different drugs, this setup is a bit different, P different drugs, and the time to recovery is recorded. So, the problem is the following, that we have n persons suffering from a headache for the given problem. It may be for some other disease also the same approach can be applied. They are given P different drugs, and then the time to recovery corresponding to each of these persons for each of these P drugs are now recorded. Now, the data structure is of the following form in this problem. So, these are what we have as the subjects, which are these patients 1, 2 up to n, and then what we have here is the drugs. So, we have P drugs being administered. So, we have all these P drugs on this side. Now, corresponding to this person number 1, we will administer all these P drugs to the same person, and then the time to recovery from a particular headache by administering drug number 1 is put here. The time to recovery of the same patient when drug 2 is administered at some other point of time is recorded, and like this we have all the recordings taken for the first patient, and likewise for the second patient and the third, and all the patients are recorded. So, we have this data in the form of a P by n matrix. Now, what can be the point of interest in such a problem? The point of interest in such a problem for any practical purposes would be to know whether these P drugs that were actually administered, or rather P drugs under consideration, whether they are same with respect to time to recovery or not. So, we would be interested in the following problem. Let me write it. So, we may be interested in testing the hypothesis that the P different drugs are no different as regards to relief time, right. So, that is the setup of the problem. We have P drugs and we are trying to see whether the drugs differ among themselves, or there is no significant difference at all between the P drugs that were administered for this particular illness. Now, how to frame this particular problem? We would require some assumptions in order to test this particular problem. We will assume that this x, which is the time to recovery for the P different drugs, these are P random variables here. So, x1 is a random variable which denotes the time to recovery for drug number 1, x2 denotes the random variable denoting the time to recovery for the second drug, and so on. xp denotes the time to recovery for the pth drug. So, we will assume that this P dimensional random vector, this has got a multivariate normal distribution NP mu sigma, where each of these elements here mu 1, mu 2, mu p, they are the mean time to recovery for the P drugs. Now, what is the null hypothesis in terms of this multivariate normal distribution assumption? The null hypothesis would be mu 1 equal to mu 2 equal to mu p. This is to be tested against the alternate hypothesis HA that they are not equal. That is, the alternate hypothesis is not H naught. Now, in terms of what we have framed here, I will be able to write this in terms of an alternate hypothesis that I will say for the moment it is A mu equal to a null vector against the alternate hypothesis. Let me write first as H naught prime and H A prime against the alternate hypothesis that A mu is not equal to a null vector. What is my A? My A is a P by P minus 1 by P matrix of constants, which is going to be given by the following, that the first entry here is 1, zeros here, minus 1 here, so that when I multiply this A by mu, what we will be having at the first element is mu 1 minus mu p, that's equal to 0, so that we will be able to say from this first line that mu 1 is equal to mu p. The second would be mu 2 equal to mu p, and likewise mu 1 equal to mu 2, mu 1 equal to mu p, mu 2 equal to mu p, and so on. The last, that is p minus 1th row of this matrix of constant, this will be minus 1, and the previous element would be 1. So, this will lead us to, if we look at what is A mu equal to null, this would give us mu 1 equal to mu p, mu 2 equal to mu p minus 1 equal to mu p. So, all of them basically are equal. So, mu 1 equal to mu 2 equal to mu p, this hypothesis is translated in terms of this hypothesis. So, with this as A, we will have this particular problem being carried forward by defining a new set of random variables. A random vector y is defined as A times x. Now, this is our p minus 1 by p matrix of constant, and hence this y vector is now a p minus 1 dimensional random vector. Now, this is going to have a multivariate normal distribution n p minus 1, and with a mean as A mu and a covariance matrix as A sigma A prime. Now, if that is there, let us denote this by equal to a vector gamma. Now, this H naught, that A mu equal to null vector to be tested against the alternate hypothesis H A, that A mu is not equal to a null vector, is thus equivalent to this hypothesis in terms of the y random variables, y random vector. This gamma is equal to a null vector against the alternate hypothesis that gamma is not equal to a null vector. So, we have cleverly translated the given problem in terms of this random p minus 1 dimensional random vector y, which is now having this as its underlying multivariate normal distribution, and we are going to test that the mean of that particular multivariate normal distribution is a null vector against this particular null vector, that gamma is not equal to a null vector, and the testing for that would be carried forward using exactly the previous approach which we had in the previous setup, that x follows a multivariate normal with a mean vector mu and some variance covariance matrix. If we are interested in testing the mean vector to be a null vector against that it is not, then we can use the usual Hotellings T2 statistic for testing. So, from the given problem, what we had was this: in terms of x's, we will translate this particular problem in terms of y's. That is possible because given this set x1, x2, xn, given this x1, x2, xn, that is what was the original random sample, obtain this y1, y2, yn, which is going to have a dimension less now, y1, y2, yn, and based on this y1, y2, yn, we can get this y bar vector and this sy matrix, the sample variance covariance matrix that is based on y1, y2, yn, and use T2 based on y observations. And that completes the testing for this particular problem. In the next lecture, what we are going to see is to look at some important properties of Hotellings T2 statistic. Thank you.